Hello to lecture number 4. In lecture number 3, we saw immediate assertions. And in this lecture, we'll start with the basics of the concurrent assertions. In the rest of the course, these are the symbols that I'll be using. The topmost high going arrow, so to say, is what I call level sensitive high. These are my own symbols, and this I thought would be the best way to convey the timing diagrams. What level sensitive high means is that at a given clock edge, let's say the clock edge is in the middle of this arrow, that the signal was high before the clock edge and the signal is high after the clock edge. And this becomes important when we go into the detail of sampling edge and the value of the signal that's being evaluated in the pre-pone region. Just keep this aside for now. Similarly, the downward arrow says that the signal was low before the clock edge and it is low after the clock edge. Now, these are our regular timing diagram edges that you are familiar with. Now, this means that a pause edge is expected on this signal. Pause edge is expected on this signal. Similarly, a neg edge is expected on this signal. Now, in order to see whether a property is passing in a given timing diagram, I will use a green arrow going high, means the property passes, and red arrow going low means the property fails. Okay, let's start with very basics. Here's the specification. It says that at pause edge of clock, if cycle start is high, again high before the clock and high after the clock, at this clock edge, if C start is high, it implies that rec is high at the same clock and that grant is high 2 clocks later. If this spec is met, then at this clock edge, the property will be considered to pass. So let's see. First, you declare a sequence. A sequence is the keyword and sequence is the keyword. You give it a name. This sequence says that request being true at the sampling edge or clock edge, I will intermittently use them, but they mean the same thing, only that a sampling edge can be a synchronous clock edge, which is what normally people use, or for example, it can be a gated clock, which is asynchronous, but the point is it has to be an edge. So at this pause edge of clock, request being true, that 2 clocks later grant is true. Note pound 2 means 2 sampling edges or 2 clock edges. They cannot be level sensitive control. Do not confuse this with pound 2, which is 2 time units in Verilog. There is this extra pound here, so the chances of misunderstanding are low. So you have declared a sequence, then you declare a property. Property and end property are keywords. The property says that at pause edge of clock, if C start is true, start the evaluation. If C start is true, it implies SR1. It implies that SR1 should hold. Now this implication is overlapping implication, and we'll see what the difference is between non-overlapping and overlapping. Overlapping here means that the same clock edge that C start is high, that request must be high. So here's the property. Then you have to assert the property. Property on its own is just placeholder. It's not going to fire. So when you assert it, you're triggering it. And here's the syntax. You give it a label, and just like with immediate assertions, you are better off giving a label, else the simulator will assign one for you and that label may not make sense to you. So you assert the property, give it the name of PR1 in parentheses, and declare that if the property passes, you will execute this display statement, pretty much like an immediate. Else, you will execute this procedural statement. I'm just going to leave this at this stage. You have a sequence, you have a property, and you assert the property, and you give it a label. Now, I'm continuing with the same example to highlight some of the other points. I just explained that you must have an edge at which the property is to be evaluated. You cannot have level sensitive, and most of the time people use a synchronous edge. You can have an asynchronous edge, but I will caution you right now that you have to truly understand how the assertions get evaluated on an asynchronous edge. But as long as it's an edge, the language has no problem. It will allow you that. Now, the other key important concept here is that cstart is a signal, a variable. Request is also a variable, and so is grant or signals. The cstart is evaluated as passage of clock. The sequence doesn't have a clock, but it inherits the clock from this property. And we'll see a bit more on that. And so all the three variables, cstart, request, and grant, will be evaluated at passage of clock. And you have these action blocks, as they are called. There is a pass action block if the property passes, else there's a fail action block if the property fails. One important note which is slowly happening in the industry is that the simple assertions, as I call it, are synthesizable. What that means is a simple assertion like this one will be synthesized, converted to gates, and it ends up becoming part of your design, and you can go to FPGA emulation or even accelerator for that matter. And so once the assertion is synthesized, and let's say it's in the design in the FPGA, if it fires, for example, if it passes, I don't think we really care. But if it fails, how do you know that it has failed? There are so many ways that the EDA vendors have implemented their own methodology on letting you know that an assertion has failed. So, for example, here what I've done is I've taken a 16-bit register and I'm assigning it a value. And then through FPGA, you can scan out this value, and if the value is F, you know that this particular assertion failed, this is the easiest way to debug. And since the assertions again are being synthesized, it's a great boon to productivity and debuggability. Okay, what I've done is here I had request and grant as only two signals. In this slide, I have added a little bit more complication. Before we go into this, I want to point out that this cstart, something that appears before the implication operator, is called antecedent. This is the implication operator, and then anything that appears after the implication operator is called consequent. So you will hear me say antecedent fired, consequent failed, so on and so forth. So you know what that means. And this, going back to this one, all I'm pointing out here that it can be a very useful and very complex Boolean expression. And it's interpreted the same as a conditional expression of the procedural if statement. And just like a procedural if statement, if the Boolean expression evaluates to X or Z or 0, then it's considered to be false. That means the property will fail. So that's all in this particular slide. And One more point here, that this Boolean expression can also include function calls. So the point is that in the sequence you can have temporal domain like we have on prompt 2, and you can have very sophisticated expressions including function calls. Going back to the implication operator, like I was telling you, that this slide, let's go back here. Here I have a sequence with this particular Boolean expression. In this slide, what I've done, and in this slide, this Boolean expression occurs in a sequence, and then we call the sequence here. What I'm trying to point out is that you don't have to have a sequence in your design of your assertions. You don't have to have it. You can take that entire Boolean expression and put that directly into the property. If it is a simple expression, then it's okay for you to do this. But I highly recommend that a complex property should be broken down into smaller sequences. When you read a given spec, the spec may look daunting and you may start scratching your head on how am I going to model this assertion. Take smaller portions of the spec, create sequences of those smaller portions, and then tie them all together. Have hierarchical sequences too. We'll see more about that. And then tie them all together, and then in a property define what I call intelligent antecedent and fire the consequent, which will have a sequence here, which will call one sequence, which may call another sequence, so on and so forth. So I will show you exactly how I break down complex specs into smaller sequences and then design the assertion. It will be much easier to design and much easier to debug. So what we have seen is you have Boolean expressions. Those are used in sequences. Boolean expressions can also be used directly in a property like I just showed you. But this is what I call the language hierarchy. Try to follow this hierarchy for you to be able to design assertions with ease. Then there is the property, and then there is the assert statement. There is also a cover statement. There is also an assume, and there is also an expect. You can assert a property, cover a property, assume a property, and expect. And we will see cover, assume, and expect in much more detail in coming up lectures. Again, going back to the implication operator. Like I said in a previous slide, this single dash here is the symbol for overlapping operator. And overlapping means that whenever the antecedent fires, that the consequent starts executing or start firing at the same sampling edge, which is pause edge of clock here. As you can see in our example, that this implies that whenever C start is high, the request must be high. And then 2 clocks later, grant must be high. Opposite to that, or not opposite, but a variation of that, is non-overlapping operator. And the difference between the symbol is here you have a dash, while here you have an equal to sign. What non-overlapping operator says is that if at a sampling edge, which is pause edge clock here, antecedent is true, if C start is true, they're starting the next clock, not the same clock. Starting the next clock, you sample request to be high. And then 2 clocks later, you sample grant to be high. And the word sample is important. I won't use the word detect, sample, because you will see what sampling means at the sampling edge in the preponed region. We haven't covered that yet. So just keep that in your back pocket. So here, that's the difference between overlapping. Overlapping is that the consequent starts at the same clock edge, while non-overlapping is where the consequent starts at the next clock edge. Let me show you a very simple use. Now, overlapping means start at the same clock edge. Sample start consequent at the same clock edge. But if you put pound 1, that means start at the same clock edge, but wait for 1 clock before you start executing the consequent, which is the same as you can see as non-overlapping operator. And I'm pointing this out, which I'll explain in just a second. So the point is here, if you use this, it is the same as non-overlapping operator. Now, let me give you a project-wide hint or suggestion. As you can see, overlapping operator is a subset of non-overlapping. In a project-wide methodology, if you don't have guidelines, then some people may use non-overlapping, some people may use overlapping, some people may use overlapping with a pound 1, some won't. When you are debugging, unless and until you have another screen with exact assertion in front of you, if you are looking at the timing diagram, you do not know what is expected. Is it the overlapping that is expected or non-overlapping? So my suggestion is that use overlapping. It is a common denominator. Use overlapping and then use pound 1 if you want the effect of non-overlapping. You cannot go from non-overlapping to overlapping, but you can go from overlapping to non-overlapping. And then project-wide methodology, you can suggest that everyone uses only the overlapping operator and then use a pound 1 if you want the effect of non-overlapping. That way, when you're debugging, you know that the antecedent and the consequent are implied, their implication relationship is overlapping all the time. And that will definitely help you even design and debug your assertions project-wide. So I'm going to leave this at this stage. You saw the basics of the concurrent assertions, you saw the sequence, you saw the property, you saw how to assert an assertion, you saw the implication operator and the different styles of implication operator. We will see a lot more on sequences and properties and antecedent and consequent. So thanks a lot for attending this lecture, and I will soon see you in the next lecture.